I guess I'll start now, and if anyone wants to join later, then I guess they can join. Okay, so today is ALP. So this is week 2 of the ALP Combinatorics lectures. Last week we covered elementary counting techniques, and this week we'll be covering more counting, which is basically permutations, combinations, and and the principle of inclusion and exclusion. If you look at the handout for this week, they also cover recursion, but I decided not to teach recursion today because it would just be me teaching so many things and no one would keep up. So it's best to focus on a few things instead. So I'm the one teaching, as you can probably tell, and my TA is Caitlin. So anyways, what will we do? So today we will talk about, so first of all, we'll review factorials a little bit, in case you don't know what factorials is. Factorials are essentially the main component of counting permutations, which are counting things with its permutations are ways of counting things where the order of the things counted is something that matters, and combinations are ways of counting things where the order of the things that are counted does not matter. So when I first learned this, a while ago, it was very confusing. Like, what does the order matter? Order doesn't matter. Like, what does that really mean? So hopefully that'll be something that I'll try to clear up today. And we'll talk about stars and bars and other things you can do with combinations and permutations. And if we have a little bit of time, we'll go through the principle of inclusion, exclusion, also known as pi, which is one of those things in math, which is a simple concept, but people use big words to describe it and make it look really scary for basically no reason. So anyways, so okay, so why not recap what we did last week? So last week we talked about like the 3 main techniques in counting, which are constructive counting that's all about adding, right? So that's all about adding. And then we also talked about complementary. Wait, no, constructive counting is about multiplication. I'm sorry. It's when you construct and what you're counting, like element by element. You sort of build it from the ground up. Complementary counting is all about subtraction. So complementary counting is where you take the total and then you subtract the things you don't want and you get the things that you do want. And casework is all about adding. So casework is all about counting one. You're splitting whatever you're counting into several groups, and you're counting each of these individual groups up and summing the result together to get your final result. So today we'll be focusing mostly on adding and multiplication, less so on subtraction, right? Subtraction isn't something that we'll be talking that much, although we will talk a little bit about subtraction when we get to principle of inclusion exclusion. And we'll also introduce how we use division, because I didn't bring it up last week. We didn't focus on it really, but division is also a big part of counting, where you know that every single thing is over counted a certain number of times. So you just divide by that and you get something where everything that you want to count is counted exactly once instead of over counted. So okay, so on to factorials. So this should be review for most of you, but factorials show up everywhere. Factorials are all about multiplying the integers from 1, 2, 3, 4, all the way to some integer n, and then you take the product of those, and then you get the factorial of n. So you can see here, so for example, 5 factorial is equal to 5 times 4 times 3 times 2 times 1, which is equal to 120. So factorials are really important when it comes to constructive counting, right? Like the multiplying things together. You might have 5 ways to do to construct the first element, 4 ways to construct the second element, 3 ways to construct the third element, and you keep going in this way. Like you're constructing your element piece by piece, and when you do that, a lot of times you're going to get a factorial as your final result. So those are factorials. Okay, so the main concept that I really want you to grasp fully, because this is very important, is the concept of order. And the idea of order it's a little bit tricky to get. It's something that you have to get by just thinking about it more and more in your head, running through examples like where does order matter, where does order not matter. If you keep walking it through your mind, and then you just yeah, so you should, it's all about thinking about it again and again and again in your mind. At least that's how I learned the concept of order. But anyways, so okay, so how do I figure out? So a lot of times you want to, so a lot of times essentially the order in where things are placed among each other matters. So one way to think about this is that let's say you have a word, right? Like, I don't know, like let's say what kind of word. So maybe something like whatever. So okay, so let's square. Okay, square. So the order, so the English language is an example of something where the order in which you place the letters in whatever you're writing matters. Otherwise, if you get the order wrong and you write something like UA QS ES R, something like this, then you just end up with a bunch of gibberish, right? Because the order in which you place the letters is very important in what in the meaning of whatever you're writing. So when you're formulating a word, and this is an example of something that you do where the order in which you place the letters is going to be something that matters. So on the other hand, let's say maybe like when you're let's say you're paying for something or something, and you're paying for something, and then you might have to pay like a dollar or something. I don't know, it's probably a stupid analogy, but a dollar and a quarter. So you can pay the dollar first, and then you can pay the quarter second, or you can pay the quarter first and the dollar second, and it's not going to matter in which order you pay them, because you're still paying the same total amount of money. So this is an example where when the order in which you do the things doesn't really matter at all. And then both of them, both ways of doing that thing, right? Doing things in one particular order and doing things in another particular order, they can be counted as the same exact thing. So that's an example where the order in which you do things does not really matter at all. It's just what you do. It doesn't matter when you do it, or like what order you do them in. So if you do things in order, and the order matters, then we call this a permutation. So permutation is a permutation, for example, a permutation of the letters SQUARE could be something like SQUARE or UAQESR. So these are different permutations of the same set of letters, the same set of 6 letters. So order matters. Combinations are things where the order doesn't matter. So the order in which, so these are just, you can think of these like the money you pay with, right? You can just think of them as combinations of currency, right? Different types of currency. You can think of them as combinations of currency. You can't really put the currency in some order. They're still the same set of currencies, right? So this is the example of a combination. It's just a combination of different denominations of currency. So that's an example of a combination where the order does not matter. So this brings us back to an idea of basically what, in a counting problem, one thing you really have to get straight is whether some things are counted as distinct or are they counted as the same, right? So this comes up a lot in a lot of problems. Sometimes you have problems where like you've seen like these annoying problems where they say like rotations and reflections are considered identical or distinct, right? I always see people mess up on these problems where like rotations and reflections are counted as identical, distinct. Rotations are counted identical, reflections aren't, right? So this is all about, so these problems, right? They're all about thinking deeply about whether you're going to be counting something once, twice, or like none at all. These things can be a bit tricky to deal with, so you always have to be thinking through your head. Is what I'm counting distinct on its own, or is it the same as something? Was it treated the same as something that we've already counted earlier in the process, right? So okay, so that's my explanation of order, I guess. So on to, so an example of permutations, another example of permutations, right? So say 8 people are in a race. So how many ways can the ranking of these people can be decided? And we're assuming that there's no ties here. So for any 2 people, one of them has to do better than the other, right? So if you know anything about combinatorics, then this problem is very easy. So the first thing you do is you can decide the person who wins first, right? There's 8 ways to decide the person who wins first. And then there's how many ways to decide the person who gets second. So there's 7 ways to pick the person who gets second. You just choose out of the 7 people that you have left. How many ways to choose the third person? Well, there's 6 ways to choose the third person. And you keep going like this, and you decide each of these places. You decide each of these places, and eventually your ranking, right, it gets decided. Notice that once you choose everything else, the eighth person is already fixed, right? So this is an example of 8. So this comes out to be 8 factorial, which comes out to be forgot what it comes out to be 40,320, right? So this is a basic example of a permutations problem. So permutations problem, right? This is an example of the order in which the people place is going to matter. So it matters who gets first, who gets second, right? So if A gets first and B gets second, that's different from when B gets first and A gets second, let's say. And the same goes for other players and other rankings, right? So there's 40,320 rankings. So that's the number of ways that we can sort of arrange these 8 people in order to get the final ranking. So that's an example of permutations question. How about a combinations question? So 8 people are in a race, same scenario as before. There's no ties. So now, how many ways are there to choose the top 3 people, right? How many ways are there to choose the top 3 people? So the first thing that you might want to do is choose the first person in the top 3. So there's 8 people. No, there's 8 people out of which we can choose the person who's in the top 3. All right, so first person in the top 3. How many ways to choose second person in the top 3? So there's 7 ways to choose the second person in the top 3 because we've already decided one of them, right? We already decided the first person. And then we go on to the third person in top 3. There's 6 people to choose from to decide our first person, right? So however, there's a catch in the fact, and so to see why we can't just multiply these and get the answer of 336. Why is this wrong? To see why this is wrong is because, let's say we have 3 people, A, B, C. So how many ways have we counted, right? How many ways have we overcounted this, the configuration where A, B, C are all in the top 3? So one way we could have counted this, how many ways did we count this? How many ways did we count this? So one way we counted this is by choosing A as the first person, B as the second person, and C as the third person, right? Another way we could have counted this top 3 group, this podium, right, is if maybe like A was the second, B was the first, C was the third, where A was the third, B was the second, C was the first, and so on, right? We've overcounted this single top 3 choice, right? This top 3 group. We've counted this group. We've actually counted it 3 times 2 times 1 equals 6. We've counted this 6 times. We counted this 6 times. And to see this we could have thought about just like how many ways can we arrange A, B, C in order. That turns out to be an equivalent problem to asking how many times have we counted this top 3 groups. And the reason why we've counted this top 3 group 6 times instead of only 1 time is because we've counted them in order. We've acted like there's some sort of order in the group. We chose the first person, then we've chose the second person, then we've chose the third person. But in reality, the first person, second person, third person, right? It can be in any order. So in this case, we just need to choose the top 3, the group that's in the top 3. So the order in which these top 3 come in, right? The order in which these come in is not going to matter. They're all going to be counted as the same exact configuration, right? They're all going to be counted as this group of 3 that's the top 3. So we've counted this 6 times. So this is where division comes in, right? So since everything is, so if we let c be the number of bad variable choice, if we let n be the total number of ways we can choose the top 3, 336, that ends up being 6 times what we want, right? Because each thing in n is counted exactly 6 times in our count of 336. So what we have to do is divide by 6 on both sides, and we get 336 over 6, which becomes 56. We have 56 as an answer. And you could also complete this directly as just 8 times 7 times 6 over 3 times 2 times 1, and just simplify from there. So again, a pretty long-winded explanation, but the key idea I want you to really focus on is the idea of the order matter and the order doesn't matter. So sometimes the order is going to matter, like when we're assigning a ranking, but when we're only choosing the top 3 out of 8, let's say, then the order in which we choose this top 3 people, it's not going to matter. We can choose them in any order and it'll still be counted as the same configuration. So okay, so that's example of combinations, right? So anyways, okay, so now there's another example of a type of problem that comes up very often, and this is about like rearranging the letters of words, right? So how many ways to rearrange letters of the word, let's say Nike, but Nike's not here, but whatever. So to rearrange the letters of the word Nike, there's 4 letters. They're all different. There's an N, there's an I, there's a K, there's an E. So we can just construct the word letter by letter, right? So we start with the first letter. There's 4 ways to choose this. Then there's 3 ways to choose the second letter. There's 2 ways to choose the third letter, and there's 1 way to choose the last letter. This comes out to be 4 factorial, and you can see that you can check on your own that it's equal to 24. So this is 24. So this covers all the different permutations of the letters of the word Nike. So we're essentially assigning a ranking to the letters. It's very, so this is where the factorial comes in again. So now onto the second where you're rearranging the letters of the word cherry. So not the spelling of the Y, the weird spelling of the I. So do you have 6 spots? Let's try to construct the word letter by letter again. So there are 6 ways to decide the first letter. There's 5 ways to decide the second letter. And you keep going. 6 times 5 times 4 times 3 times 2 times 1. This comes out to be 6 factorial 720, right? So if you weren't careful, this was what you would put as your answer. But the unfortunate thing is that R and R are the same exact letter. So it doesn't matter which R comes first, right? There's no ways to distinguish between the R's. They're identical. So if we have like, if we assign like numbers to the R's, right? R1 and R2, then we would be able to properly distinguish between something like R1, we would be able to distinguish between R1, R2 being left and right, or a word like this, right? So if the 2 letters were somehow distinguishable, then we would be able to distinguish between these 2 words. If letters were distinct, we could distinguish between these two words. Sorry for my bad handwriting. But since in this problem the r's are essentially identical, right? We take the ones and the twos away, and then we just have two instances of the same word, right? They're identical here. There's no way to tell them apart. So it turns out, as you can probably see, that each in our count of 720, we've counted every unique word exactly 2 times. How many times did we count each word? We counted it 2 times, right? 2 times. So we have to divide by 2 to account for that. So we divide by 2 and we get 360, and 360 doesn't turn out to be right. Okay? So another example, right? Square man. So earlier when we just had square, and the answer would just be 6 factorial, but now we add extra man, and it turns out that the letters A and A, they're duplicated, right? So I'll spare you I'll spare you hearing my boring voice say 9 times 8 times 10, whatever. We start with 9 factorial, and since that's the total number of letters, 9 letters, there's 9 ways to arrange them in some order. But since the A's are indistinguishable, we have to divide by 2 factorial, just 2, to account for this overcount by a factor of 2, right? So this should come out to be 181,440, if I'm correct. So 9, so that's the number of ways to rearrange letters of the word square man, where the A's are counted as identical. And these problems can be, this idea can be extended where there's like more than one identical letter, right? Maybe like the A can appear 3 times or 4 times, or maybe we have something like banana, right? Banana, where like A is seen 3 times, and then the N is seen 2 times. I won't go through these examples because even though they're a little bit more complicated, they're essentially the same idea. Okay, so on to the next thing I want to cover, which is path walking, right? Path walking. So path walking is something else that I see that you're going to see decently often on competitions. So the basic idea in path walking is, like, the basic example, I guess, is where you have a sort of like a lattice, like a square grid, right? Like a square grid of like squares, I guess. Maybe like you can think of it as being in the coordinate plane or something. And you basically have these lattice points which are like spaced 1 unit apart from each other. So this is like 1 unit, there's also 1 unit, and so on. So you have a point where you start at, and you also have a point where you want to end at. So you have like, usually you'll come up with some funny story, like I don't know, a frog starts at the starting point, and then on each move or whatever, it can hop up 1 unit to another lattice point, or it can hop right 1 unit to another lattice point, right? So we can hop right. So in this case, right, the frog can hop 1 square up to here, or it can hop 1 square right to here. And so each turn, right, it either goes up 1 or right 1, up 1 or right 1. So one, and eventually it needs to end up at the endpoint right over here. So the question essentially is asking you how many distinguishable paths allow you to travel from the start point to the end point using only a series of up and right jumps, right? So one way you can travel from the start to the end is just go do a very boring path. Go right 4 steps and up 4 steps, like this, right? Another path you can do, also very boring, is go up 3 steps and then right 4 steps. And then another path you can go is like up 1 step, right 1 step, right 1 step, up 1 step, up 1 step, right 1 step, right 1 step, so on. And then all, so these are just 3 examples of possible paths you can take. So if the endpoint is really close to the start point, then the number of ways to count a number of paths is going to be pretty easy. It's just going to be, but if you put the endpoint somewhere farther away, like for 3, then it's going to be a little bit harder to count. So how can we possibly count the number of ways we can travel? We can jump from this unit to all the way to this unit, right? How can we possibly count the number of ways that we can choose the path for the frog? So the trick is that we can look in, so the first thing, yeah, so this is a very general idea in combinatorics problems, is you're supposed to look at something that always stays the same, something that's the same across all of the paths. No matter what path the frog chooses, there might be some constant attribute, some characteristic that's always the same across all of the different paths. This is called a monovariant, or just an invariant for short. So we're looking for something that always stays the same no matter what the path the frog is going to choose. So in this case, something that you might notice is that the frog is always going to take 7 steps. The frog is always going to take 7 steps. And if you look even closer, you'll see that the frog always takes 3 steps up and 4 steps to the right. It's always going to do this. It's always going to take 3 steps up and 4 steps right. What distinguishes the paths, what makes the paths different from each other, is the order in which he does these up and right steps. But the number of up steps is always the same, and the number of right steps is also always the same. So we can think of it as rearranging, I guess you can think of it as rearranging 3 up steps and 4 right steps, right? We're arranging 3 up steps and 4 right steps. So one way, so the way I would like to, so the way we can think about this is just to have like 7 blanks for our 7 steps, and we're going to choose free spots where we have an up step, and the rest is by default a right step. So free of these steps is going to be an up step, and the rest is going to be a right step. So this turns out to be, so to compute this, we first have 7 times 6 times 5, right? We first place the first up step, then we place the second up step, then we place the third up step, right? But then we also have to divide by 6 because the order in which these up steps are placed does not matter. So if you have like up step here, then we place the second up step here, and then the last up step there, it would be the same as if we had placed the first up step here, the second up step here, and the third up step there, right? It would be the same path. They would correspond to the same path. So each path is counted exactly 6 times in our count of 7 times 6 times 5, which is 210. So we have to divide by 6, and that should come out to be 35. Sorry, my work is all over the place, but you get the idea. So basically we place the first up step, the second up step, the third up step. We divide by 6, and then once we divide by 6, we have every possible path counted exactly once. So, okay, so this, all right, so now let's look at a slightly more complicated example. Oh, you want me to replace frogs with squirrels? Okay, so okay, so let's say we have a squirrel at this start position, and it wants to go to the end position, right? So, okay, let me add a page before, a new page. Sorry, and so start and end. So we have a squirrel at the start position. The squirrel wants to get to the end position, and then at like say this point, at this point, 2 1 on say at this point 2 1, there's like something, there's like a predator. There's a predator here, right? Something scary here, like something very scary. Maybe like, I don't know. What eats squirrels? I don't know. Maybe a hawk or something. I don't know. I don't think hawks eat squirrels, but that's beside the point. So for whatever reason, the squirrel cannot pass this point, right? The squirrel cannot pass this point as it goes from its start position to its end position. So how many paths, it's asking you how many paths avoid this red point, How many paths avoid this red point? So we start with, so the first thing you start with is your 35 total possibilities. So we're gonna, for this problem, we're going to think about complementary counting here. So we're starting with the total, which is 35 total possibilities, and you're subtracting the bad paths, the paths that would lead you to get eaten by whatever is at the point, right? The red point. So you're subtracting the bad paths. So how many bad paths are there? So the first, so to a bad path is going to travel so bad path goes from 0 0 to 2 1, and then it's going to go from 2 1 to 4 3. So now this actually becomes constructive counting, right? It becomes constructive counting here. Constructive counting, because you're counting the number of ways to get from 0 0 to 2 1, and independently of that, you're choosing the number of ways to get from 2 to 1 to 4 to 3 for free. So we can just count the number of ways to do this and then multiply it by the number of ways we can do this. So number of ways to get from 0 0 to 2 1, I'll leave it to you to confirm. It's just 3. It's just 3 ways. And 2 to 1 to 4 to 3, I'll leave it on your own to verify that the answer is going to be 4 times 3 times 2 times 1, which is 6 ways. Wait, no, wait, right? Wait, sorry. Yeah, so this should be right. So there are actually 18 paths that going through the red point. There's 18 paths. So we subtract 18 paths but from our total of 35 paths, and we get our final answer of 17 paths. 17 paths that do work, that don't get us the squirrel even. So there's still a lot of choices for the squirrel to take. So okay, so before I go on to stars and bars, I want to talk a little bit about combination notation, right? So you're going to see something like this big parentheses, right? Combination notation. So you have this big parentheses where like some big number, let's say n, is on top, and some smaller number, let's say k, is on the bottom. So usually k is between 0 and n, although I've seen examples where this is not the case. So there are many ways to interpret this combination notation. So the best way of thinking about it is the number of ways to choose k elements without order from a total of n elements, right? So let's say you had like n, like, so let's say you had n marbles. You want to choose a set of k marbles from the n marbles. So to do this, you'll see that the order in which you pick out the marbles, right? The order in which you pick up the marbles doesn't matter. So it doesn't matter if you pick like a particular marble first, second, third, fourth, fifth, or even last. The order doesn't matter. The order doesn't matter here. So the number of ways to do this turns out to be n factorial over k factorial times n minus k factorial, right? So, and we go into a little bit more detail on why this actually comes out to be the case in our combinations permutations handout, but just but I think you already have a pretty clear intuition about why this turns out to be true based on the examples we've been doing already, right? Because those were also all combination problems. So the basic gist of it is that to choose, so you just choose n times n minus 1 times all the way up to n minus k plus 1. There's this many ways to choose them with order, and then you just divide by k factorial, divide, because that's how many ways each configuration is counted in this count, right? That's the number of ways each configuration is overcounted. So we start with, so I like to think about it is that the way I like to think about this formula is this component is all about if we still had order, right? If we still had order mattering, then this would be our answer. But we have this component dividing by the k factorial to make sure that, so we divide by this, so everything is order not mattering, right? So essentially the formula has two components: the component that counts what we want if order mattered, and then we divide by k factorial so that everything is counted exactly once instead of k factorial times. So that's combination notation. And choose k equals n factorial over k factorial times n minus k factorial. So I guess a few basic examples, right? Because we want some, I guess we should try out some examples of this. So let's say n choose 0, right? What does n choose 0 come out to be? So then this just becomes n factorial over 0 factorial times n factorial, which equals 1, right? And this makes sense. The total number of ways to choose 0 objects out of n objects is always 1. Just choose nothing at all. And another, you can also choose n choose n, and I'll leave it to you to verify that n choose n is also equal to 1. And in general, it's known that n choose k is equal to n choose n minus k for all k in this range. And this actually follows from our definition, over here. But you can also think intuitively it makes sense, right? Because instead of choosing k elements out of n elements, another way, an equivalent way of counting this would be to choose n minus k elements out of n, and then let our k element set be the set of elements that we didn't choose, right? So these are the same things. These count the same thing. These count the same thing. So this fact that this property that n choose k is equal to n choose n minus k can be proven algebraically using this formula. I'll leave it to you to verify that, or we can think of it as with a combinatorial interpretation, and see why these are actually counting the exact same thing. So of course they're going to be evaluating to the exact same thing as well. So anyways, on to the next thing, which is stars and bars, right? So okay, let's start off with a question. So how many ordered triples of non-negative integers x times y times z are there such that x plus y plus z equals 10. Right? How many ordered triples are there such that x plus y plus z equals 10? All right. So obviously you can just bash this out and just count directly how many ordered triples of non-negative integers are there that sum to 10, but that would be a stupid idea, and you'll be there for a long time, and you'll probably get the wrong answer as well. So this is like a fool. But there is a very smart way to count the number of ordered triples of non-negative integers with this property. And the first thing you have to do to find out how to count this effectively is to note that there's order, right? So the triple 5, 6, 10 is counted the same as 6, 5, 10, right? No, it's counted differently. So these are different. And you might ask why can't we just divide by 6 to get the number of unordered triples? And that's because you have things like 3, 3, and 4, right? Where like 2 of the elements are the same. So this is only good. This will be counted. We can't just divide by 6 to get the number of unordered triples, is what I'm saying. But anyways, back to the problem we're dealing with, which is how we find the number of ordered triples of non-negative integers with this property. And the way we do this is by having, so the way we do this is through stars and bars. So let's say we have 10 stars. Stars are just asterisks, I guess, in this row. And this, and we're gonna insert dividers or bars among them. So maybe a bar can go here and a bar can go here, or maybe we can have a bar going here and a bar going here, or maybe something very stupid where like both bars are on the left hand side, or something like this, right? Or maybe they're here between us. And the key idea is that so we're inserting 2 dividers among them, and the key idea is to notice that each possible way we can insert them corresponds with one ordered triple. So each ordered triple of non-negative integers is going to correspond with exactly one way of arranging these 2 bars, these 2 dividers among these 10 stars. And each way we place dividers among these 10 stars is going to correspond back to that ordered triple of non-negative integers summing to 10. So how is this going to work, right? How is this going to work? So the first thing we do is, so we so how is this bijection going to work? So our three numbers be the number of stars before the first divider and the number of stars before second divider after the first, and number of stars after second divisor, divider, right? So we've split our 3 stars into 3 groups. And the key idea is that by summing the numbers of stars in each of these 3 groups, we get an order triple of non-negative integers that sums to 10, right? Because there's there's 10 stars in total. So that's going to correspond with a unique order triple of non-negative integers that sum to 10. And we can construct this backwards, right? So this goes both ways. If we started with the order triple 307, then we can reverse construct this configuration by having 3 stars, then a bar, then 0 stars, then a bar, then 7 stars again. So this idea of taking some problem that's hard to deal with and transforming it into a problem of placing dividers between stars, that's what stars and bars is about, right? We have these stars in a row, and we're placing bars among the stars, so to divide the stars up into different groups. So the question becomes, how many ways to place the bars? So in this case, it becomes the number of ways to choose 2 objects, 2 bars, out of 12 total places in which the 2 bars can be. So our final answer turns out to be 12 times 11 over 2, which comes out to be 66. So stars and bars, it's a little bit tricky to understand. I probably didn't explain it in the best way, but the main idea is to start with a problem that's a little bit hard to compute. You rephrase the problem, you find a bijection from that problem to counting the number of ways counting how many ways to place some number of identical dividers among some number of identical stars. So that's the idea of stars and bars. So the bars are identical. Bars are identical. And the stars also have to be identical for this to work. So sometimes you might I see some people mess up when they might do like 12 times 11 and forget to divide by 2. Something like that. Some stupid mistake like that. So anyways, that's stars and bars. So it allows us to count. So these partition questions, right? Partitioning some number into several integers in a particular range. These problems are most often solved with this stars and bars technique, right? All right, on to the next questions, next topic, which is pi, which is the principle of inclusion and exclusion. So first of all, inclusion means when inclusion is all about including something in our account, and exclusion is all about removing something from our account. So principle of inclusion and exclusion is all about including some things in our account, then excluding them out, then including them back in, and excluding them back out again. So let's think about this more. So we want this goes back to the fundamental idea of we want everything to be counted exactly once, right? We want everything to be counted exactly once, not twice, not 3 times, not 4 times, not 0 times. We want everything to be counted exactly once, and that's the only way that we're going to get a correct answer. So sometimes to do this, is we have to overcount, then subtract to compensate, right? We want to overcount and subtract to compensate. But sometimes when it comes to the principle of inclusion and exclusion, we have to overcount and subtract to compensate. Then we've undercounted something, so now we have to overcount again, then subtract, then overcount, then subtract again, and so on. So principle of inclusion exclusion is all about adding some things, then subtracting some other things, then adding some other things, and subtracting other things, and adding some things, subtracting other things, and so on and so on and so on. Your brain is fried. It's all about inclusion, which is all about adding things, then excluding them back out again. And the ultimate goal is, after all is said and done, is that everything is going to be counted exactly once. So by now you might be wondering what the heck is this guy talking about? But anyways, so the main way we visualize this, I guess, the main way we think about this is through Venn diagrams. So let's take a look at this Venn diagram, right? This Venn diagram. So you might be asking, so let's say we have some items in this Venn diagram. So we have like some elements in one circle, some elements in another circle, and some elements are going to be in both circles, right? Some elements are going to be in the intersections of the two circles. So so how can we count how many elements there are in total? How many ways can we count how many elements there are in total? So the main way, so you might want to just count them one by one, right? You might just want to go like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and so on, like some kind of idiot. But fortunately, if in the principle of inclusion and exclusion, sometimes we can find a better way to count this. So the number of elements that are in total in this Venn diagram is the number of elements in the first circle plus number in the second circle, and then you subtract the number in the intersection. So why do we subtract the number of elements in the intersection? So if we count the number of elements in the first circle, then add the number of elements in the second circle, then each element in one of these outer regions, right? Each element in one of these regions, it's going to be counted once, right? It's going to be counted once for whatever circle it's in. However, each element in the intersection over here is going to be counted twice. It's going to be counted once for the red circle that it's in, and once for the blue circle that's also in. So now we have to subtract the number of elements in this intersection in order to count. So we have to subtract the number of elements in this intersection in order to make sure that every element in this Venn diagram of sorts is counted exactly once with no repeats, right? So now let's onto a more complicated example with these three circles, right? With these three circles. So okay, so I might just draw these three circles again. So we have the so you have the green circle, you have the green circle, and then we have the purple circle, and we'll say we have the pink circle, So how many? So we want to find out how many elements there are in total. How many elements there are in total? So once again, one way we could do this is just count all the elements up one by one, but that's no fun. And you're bound to mess up somewhere. So oftentimes we'll know, so the principle of inclusion and exclusion is going to tell us that the number of elements there are in total is the number of elements in green circle plus the number in the purple circle plus the number in pink circle. Then you have to subtract a bunch of things, right? Because in the intersections, right, we've essentially we've overcounted a bunch of things. So now we have to subtract the number in the green. Oops, wrong column. Sorry. The number in the green and pink, right? Minus the number in the purple and pink, and then minus the number in the green and purple, right? So now we can subtract what we're doing is that we're subtracting the intersections of the two circles, because everything that's only in one circle, right, we've only counted it exactly once, so we don't have to deal with these anymore. So we subtract a number in the green and the pink, we subtract a number in the purple and the pink, and we subtract a number in the green and the purple. So now everything that's only in one circle is counted exactly once, and everything that's in exactly two circles, that's in exactly two circles is also counted exactly once, right? It's counted once for each circle that it's in. Then we subtract one of these copies for when we subtract the number of elements in each of the pairwise intersections. But now it turns out that we've actually undercounted some more. And what we've undercounted is the set where that's in all three of the circles. We undercounted the set that's in all three of the circles. That's this intersection. So we have to, so how many times have we counted each element here, right? In each element in this center intersection thing, right? So each element in this part of the Venn diagram is counted once in the green circle, once by the purple circle, once by the pink circle. It's subtracted once by each of the intersections, right? We have, because subtracted once for the green and pink, subtracted once for the purple and pink, subtracted once for the green and purple. So it turns out that we've actually counted this 0 times. We've actually undercounted this, so 0 times. So we have to add back again the number in all circles. You have to add it back again. So now that we've added it back again, we'll see that now finally everything is counted exactly once. Everything is counted exactly once. All the elements, so everything is now counted exactly once. right? So everything in the green circle only is counted exactly once. Everything in the purple circle only is counted exactly once. Everything in the green, purple, but not the pink, it's counted exactly once. Wherever region you zoom in, we've done our including and excluding such that everything is counted exactly once, no matter what region it's in, right? So we've gone through all this trouble to make sure that we've gotten the correct count. We've made sure we've not overcounted or undercounted. So that probably, listening to me explain this probably gave you a big headache, but you should think of the principle of inclusion and exclusion as not as like a theorem, but just a general, as the name states, a principle, right? It's a general strategy. So it's a strategy, not a theorem. And because and you should think of it as a strategy because there's many different ways of applying this general idea of including some intersections, excluding some intersections, including some things, excluding some things. You can think of it as a strategy. You should not think of it as a theorem, because the theorem implies that there's only like one way to use it, when in reality there's a ton of ways to use the principle of inclusion and exclusion. And sometimes you're not being asked how many elements there are in total. Sometimes you might be given how many elements there are in total, and you have to solve for like the number of in a particular circle, right? So you're not always finding the same thing. You're not always looking for the same thing. So you should really think of the principle of inclusion and exclusion as a strategy for how we get every element in what we want to count counted exactly once, and we're not counting anything else, and we're not missing anything. Okay, so general pi, I'm just gonna leave out. I don't really have the energy. If that, you can read it over handout later. So onto an example, right? So how many positive integers less than 100,000 are a square or a cube? Yeah, so how many positive integers less than 100,000 are a square or a cube? And I actually sillied a similar question on the DMC10B, right? I sillied a similar question on the DMC10B. Instead of getting a 150 out of 144, how tragic. But anyways, these problems are very easy to silly, because one thing that you may be inclined to do is just count the number of squares plus the number of cubes, right? You might just be inclined to count the number of squares plus the number of cubes. And that's what I did, and I got the wrong answer. And the reason why you can't just do this, the reason why you can't just count the number of squares and add onto the number of cubes, is that you've counted one type of integer exactly twice. You've counted the number of sixth powers exactly twice. So you can think of it as like a Venn diagram, right? So we have the squares, you have the cubes. In this intersection, you have the sixth powers, right? So you want to count everything exactly once. So to do this, you have to count the number of squares plus the number of cubes. Then you have to subtract back the number of sixth powers, and then you would have everything counted exactly once in your final count. So okay, let's go about this, right? So the number of squares. How many squares are less than 100,000? So that, to find this, you can just go, what's the square root of 100,000? I guess if you calculate enough, you'll get it to be 316 point something, 0.2, according to my calculator. So there's going to be 316 squares plus how many cubes, right? So you just take the cube root of 100,000 and you get 46 point something. So there's 46 cubes. And then you subtract the number of sixth powers, and it turns out that there's only six sixth powers. So you subtract 6, and then you get your final answer, which is going to be 356. So now you've counted everything exactly once. How many positive integers in this range are a square and or a cube? Maybe it would have been more obvious if the question had said and or a cube. You might have just, a lot of people are just going to forget that a number can be a square and a cube. What a concept. So anyways, 356 is the answer to this question. So on to another example. So, okay. So, all right. So so, all right. So this is an example from the 2017 AMC 10B. So call a positive integer monotonous. I guess you can call my voice very monotonous. If it is a one-digit number, or its digits read from left to right, from a strictly increasing or strictly decreasing sequence. So the question is asking you, how many monotonous positive integers are there, right? So, okay, so the first case, all right, so the first case we want to count is the monotonous numbers with the digits in a increasing order, right? So increasing order. So the key idea here is that the number of ways to choose the number of a positive integer where the digits form a strictly increasing sequence is actually the number of ways to choose a non-empty subset of the digits 0 through 9, 0, 1, blah, blah, all the way up to 9, right? So, okay, so yeah, so if you want to choose a non-empty subset of the digits 0 through 9, okay, you also can't have your number be 0, right? You can't have your number be 0. So the number of ways you can choose a non-empty subset of digits from 0 to 9 is, without it being non-empty or without it being 0, it turns out that it becomes 510 if I'm correct. 510 if I'm correct. Let me see. Wait, sorry. Wait, I messed up. Sorry. Okay, so non-empty increasing order. It's 1 through 9. choose a non-empty subset of the digits 1 through 9. You can't choose the number 0 because 0 would just end up being a leading digit. So I guess I screwed up there. But anyways, so once we got this non-empty subset, right, it's always going to correspond with a digit, with a positive integer with digits in strictly increasing order, because we can just order the integers in the subset from least to greatest to get our final positive integer. So our total number of ways is 2 to the power of 9 minus 1, right? That becomes 511, not 510, you can't. Which is 0. All right, so now what about decreasing? What about decreasing? Where? So this is the number of ways to choose a non-empty subset of, now there's 0 to deal with, 0 through 9, that is also not 0. So as long as it's not just 0, we can always order the digits from ascending, from the greatest to the least, in order to get an integer whose digits are in descending order, right? So the total number of ways to choose a non-empty subset of this type is going to be 2 to the power of 10 minus 1, because we have to subtract the empty set. We have to subtract the set that's just 0, because we're only dealing with positive integers here. So now we have 1022 integers of this type. So if you were unwise, you would have just added together 1022 plus 511 equals 1533, and what that would have been an answer choice on the actual thing. So we would have put that in and you would have gotten the wrong answer. Then you would have been very sad because this is not the correct answer. And because some integers are in both. Some integers have their digits forming a strictly increasing or a strictly decreasing sequence. And these integers are precisely the one-digit integers, number of one-digit integers. So there are 9 of these. So you subtract 9, you get 1524, and that should be the correct answer. All right. So once again, this is another example about how you should really be treating the principle of inclusion and exclusion as not really a theorem, but more of a general strategy, general guideline to follow. How do I get each thing to be counted exactly once and only once, right? So I have a few more questions, but we're just about out of time. So I guess I'll just wrap up. So what did we do today? So today we covered permutations. The key things to know about permutations is that they're all about order matters, right? Order matters when you're dealing with permutations. So you can think of it as like rearranging distinct letters, right? Or like assigning a strict ranking, right? From best to worst. That's an example of where the order of the elements matters, right? Combinations are when order does not matter. So that's so the analogy I gave was maybe we're trying to maybe you're trying to pay some combination of denominations to pay a certain total, a certain fee, right? So in this case, the order in which you pay the items doesn't really matter as long as you pay the amount that they're asking for. So that's an example of combinations. The other thing that I might not have touched on as much is that combinations and permutations, you can't really you can't really, so sometimes a problem has elements of both. It's not always so cut and dry, right? It's not always black and white with these. And some problems are going to have elements of permutations and combinations. So it's also about yeah, so sometimes a problem has elements of both. So some parts of the problems, right, the order of the things is going to matter, and for other parts of the problem, the order is not going to matter. So we saw this with arranging the letters of the word cherry, right? So the order in which the other letters are placed, the C, the H, the E, and the I, is going to matter. But the order in which the R's are arranged doesn't matter. So some parts order matters, and other parts order doesn't matter. So we talked about a few applications of combinations like stars and bars and path finding. And last but not least, we talked a little bit about the principle of inclusion and exclusion. So what to do for next week? So the handout should be out soon. It's written by Kevin. He's very good. He's IMO Silver Medalist this year. Congrats to him. Handout should be out soon. The video should be out soon. Ask me if you have any questions and just practice, right? If you just go through the problems, there's a lot of different problems on this topic. So yeah, so the more practice you do, the more familiar you'll be with the concepts of order and permutations and combinations and so on and so forth. But yeah, that's about it.